I'll give you the keyword to search for. GitHub, Jim White, ACL2-Jupyter. You don't want, you want this. Allow? I guess we're already connected, so am I allowing or not? Yeah, so it's just very, not going to go long into this stuff, but just the most topical thing here is I'm actually interested in ACL2. That's why it's called ACL2-Jupyter. But you get here at GitHub, ACL2-Jupyter. If you scroll on down through the README, there are the usual command line things, but I added pictures about how you can launch this in GitHub Codespaces, and they give you plenty of credits for free, so you can run this in the cloud, risk-free, for no dollars either. And if you follow these instructions, just clicking and clicking, you'll wind up with this. And I've already done most of the beginning parts of that, well, actually, I'll kind of follow the instructions. As it says, well, part of it. So Codespaces is over here, off of your menu. And if you've created a Codespace already, which is the first few clicks, but there's not much to it, but you just basically, there's a dev container JSON file in there. So when you go into Codespaces, you say, I want to create a new Codespace. You just type in Jim White, ACL2-Jupyter. And then it'll go into this long loady thing, which you don't need, because you come over here to the hamburger, and they've just added a Jupyter Lab preview, so you can skip the VS Code side of this and just open Jupyter Lab. This image is 6 gigabytes, so it does take it a while to initialize. This has already been loaded, so it's loading much faster than it would in that case. But that brings you to here, and that's really about all I have done. I haven't prepped any more to this. I kind of assume you know what SBCL is all about. But these are Jupyter Notebooks, right? And these are single language kernels. Yeah, we'll do the SBCL part first. Well, and so, yeah, I don't know what a good hello world is for Common Lisp, but that's what that is. And you know, like I was saying, you know, what I'm actually here for is ACL2, which is a computational logic for applicative Common Lisp. It's the most industrial strength computational prover in existence. It's been around for 30 years. So especially in the aerospace defense area, also VLSI, if anybody's actually run a proof to prove your FPU actually computes correctly, it's almost certainly been done in ACL2 is what was done in. And actually what we want to do, same kind of thing. And applicative Common Lisp means it's the functional subset of Common Lisp and leaves out the other stuff. So unlike a lot of these prover languages, you're doing it in the language we know and love, which is Lisp, which is going to be the #1 AI language for coding, because you can overcome the bias around taste and the dislike of parentheses as long as we get the token issue fixed. And this is in the ACL2 kernel. Import our book. I kind of consider the hello world of proving and computation to be a Quine, which, as we all know and love, is a lambda expression that evaluates to itself without any of the silliness of character encoding and reads and routes, but you can do that too. But here what we get is not only do we get the fact that it's equal, but we can say a theorem that evaluating the Quine applied to its own data is its own definition. But of course, this is not really the kind of the quintessential form. The quintessential form is that the expression evaluates to itself. So, of course, you could write this out, but it's a little bit tidier, or I like to write it this way. So again, though, we have theorem that What I don't know yet is how to write this so that it's 0 or more evals, but that's what I'd like to figure out. But I'm not an ACL2 expert, but I'm going to become one. And same kind of thing. It says it has proved that this will always be true. Anyhow, so that's ACL2. But like I say, for just common Lisp, that's here too. That's it.